You think light is simple, a wave, a particle, something physics textbooks explain in 2 pages. But when James Clerk Maxwell sat down in 1862 at King's College London and calculated that electromagnetic waves move at 310 million arn, 740,000 meters per second, he wasn't just measuring speed, he was unifying the universe. The man took electricity, magnetism, and light, 3 things everyone thought were completely separate, and showed they're the same phenomenon wearing different masks. No one had done that since Newton unified heaven and earth with gravity. And the way Maxwell figured this out, the mechanical model he built with rotating vortices and tiny idle wheels like Victorian gears, then abandoned it all for pure mathematics, is more genius than most people imagine. Here's what actually happened. 1861. Maxwell publishes On Physical Lines of Force, picking 4 parts. Inside this paper, he adds 1 term to Ampere's circuital law. 1 correction. The displacement current sounds boring. It's the hinge that opens everything, because without that term, the equations don't predict waves. Without waves, there's no connection to light. Without light, Maxwell's just another physicist tinkering with magnets and wires, but he saw what no one else saw. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They bootstrap each other through empty space, self-propagating, wave-like, moving at a very specific speed determined by 2 constants anyone could measure in a lab. The permittivity and permeability of free space. If you value documented physics and electromagnetic history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from the Royal Society's Philosophical Transactions, publishing Maxwell's 1865 paper, A Dynamical Theory of the Electromagnetic Field, which established his complete theory, going nice, and the IEEE milestone dedication documentation, published January 29th, 2024, which confirms his work at King's College London between 1860 and 1871, wows, alongside his experiments at his family estate Glenlair in Scotland. Now back to the information. Let's rewind to 1856. Wilhelm Weber and Rudolf Kohlrausch discharge a Leyden jar, the original capacitor, measuring the ratio of electromagnetic to electrostatic units of charge. They get a number spot, 1 divided by the square root of the product of permittivity and permeability, the value around 300,000 kilometers per second. Same ballpark as the speed of light. Hippolyte Fizeau had measured light at 315,000 kilometers per second in 1849. Léon Foucault improved it to 298,000 kilometers per second in 1862. The numbers dance around each other. Coincidence? Maxwell didn't think so. 1861 at King's College. Maxwell lectures on natural philosophy. He's obsessed with Michael Faraday's work, specifically the idea of lines of force filling space. Faraday sees the invisible. Magnetic fields aren't action at a distance. There's something real threading through the void. Maxwell wants to translate Faraday's visual intuition into mathematical language. But how do you model an invisible medium? Victorian solution: build a machine. Maxwell constructs a mechanical model. Picture this: all of space filled with tiny molecular vortices. Not metaphorical vortices, actual rotating cells of ether. Each one spins around an axis aligned with the magnetic field. The vortices are hexagonal, packed together like honeycomb. Between them, layers of small particles, idle wheels acting like ball bearings. The idle wheels let neighboring vortices spin in the same direction without friction. The tangential velocity of the vortices represents magnetic force. The angular momentum of the spinning corresponds to magnetic intensity. The displacement of the idle wheels, that's electric current. Sounds insane. It worked. From this gear and cog universe, Maxwell derives the equations. Part 3 of On Physical Lines of Force, published in 1861, contains the flash, the displacement current terms we talk. Equation 112 in his notation. When the idle wheels can't move freely, like in a dielectric or vacuum, they can only displace slightly against elastic forces. This displacement, changing over time, creates a current without actual charge flow, the displacement current. Maxwell writes it as the time derivative of the electric displacement field. This term, added to Ampere's law, creates symmetry. Faraday's law shows a changing magnetic field produces an electric field. Now, Maxwell's correction shows a changing electric field produces a magnetic field. The loop closes, Maxwell manipulates his equations, takes the curl of the curl, applies vector identities, out pops a wave equation. Electric field propagating through space, magnetic field propagating through space, both coupled. both moving at velocity equals 1 divided by the square root of permittivity times permeability. He plugs in Weber and Kohlrausch's measured values, gets $287 million, 980,000 meters per second from his King's College experiments, using equipment borrowed from John Gassiett's laboratory at the Lawn in Clapham. The Clapham Society documentation, published March 10th, 2025, confirms these measurements, 7.3% below Weber and Kohlrausch, 3.4% below Foucault's light measurement. Close enough. Maxwell writes in 1862, "We can scarcely avoid the conclusion that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena." Not suggests, not proposes. Can scarcely avoid. The man knows. The mathematics tells him light is an electromagnetic wave. But here's where genius doubles. 1865. Maxwell publishes A Dynamical Theory of the Electromagnetic Field in the Royal Society's Philosophical Transactions, volume 155, page 459 onward. The mechanical model, the vortices, the idle wheels, all of it vanishes, gone, stripped away. What remains? Pure field theory. The electromagnetic field exists as a fundamental entity. No underlying mechanism, no ether machinery. The field itself is real. Electric field vector. Magnetic field vector, related by differential equations. This paper contains Maxwell's final form of his equations, though not in the compact vector notation we use today. That came later from Oliver Heaviside in 1881, who reformulated Maxwell's original 20 equations in component form into 4 equations using vector calculus. 20 years pass. Maxwell dies November 5th, 1879, at Glen Lair from abdominal cancer. He's 48. Never sees experimental proof. That falls to Heinrich Hertz. November 1886 at the Karlsruhe Polytechnic in Germany. Hertz constructs a spark gap transmitter, 2 zinc spheres, 30 centimeters diameter, 3 meters apart, connected by copper wire. Central spark gap. When high voltage alternating current jumps the gap, the spheres and wire form an oscillating dipole antenna. The oscillating charges radiate. For his receiver, Hertz uses a simple copper wire loop, 120 centimeters by 80 centimeters, with its own tiny spark gap. He applies voltage, sparks at the transmitter, then, 1.5 meters away, sparks at the receiver. No physical connection. Electromagnetic waves traveling through air. Hertz positions a zinc reflecting plate 12 meters from the transmitter. Standing waves form, 4-meter wavelength. Using a rotating mirror technique, Hertz measures frequency, calculates velocity, gets a number near 300,000 kilometers per second. The speed of light, he doesn't stop there. Test reflection, refraction, diffraction, polarization. Every optical property of light. These invisible radio waves exhibit them too. Late 1887, Hertz submits his paper on electromagnetic effects produced by electrical disturbances in insulators to the Berlin Academy. March 1888, he publishes Über die Einwirkung einer geradlinigen elektrischen Schwingung auf eine benachbarte Strombahn in Annalen der Physik, volume 270, number 5, pages 155 through 170. May 1888, another paper, Über die Ausbreitungsgeschwindigkeit der elektrodynamischen Wirkungen, same journal, volume 270, number 7, pages 551 through 569. The velocity of electromagnetic propagation measured and confirmed. Maxwell was right. Light is electromagnetic radiation. Hertz performs his experiments in a darkened room. The sparks are tiny, hard to see. He measures standing waves up to frequencies around 450 megahertz, distance from transmitter to receiver up to 18 meters. The original apparatus, zinc spheres and wire loops, sits today in the Deutsches Museum in Munich, the IEE Engineering and Technology History Wiki, documenting the milestone June 14th, 2022, confirms Hertz's work between 1886 and 1888 as the first experimental generation and detection of electromagnetic waves. Hertz famously says he doesn't think these waves have practical applications. Wrong. 20 years later, Guglielmo Marconi patents wireless communication. Radio transforms the world, but before any of that technology, before Hertz's experiments, there's Maxwell sitting at Glen Lair, the family estate near Corsock in Dumfries and Galloway, Scotland. Maxwell inherits it from his father, John Clerk. Maxwell. The house, designed by Walter Newall, becomes Maxwell's sanctuary. Between 1865 and 1871, after leaving King's College London, Maxwell lives at Glen Lair full-time. He conducts experiments in spaces above the entrance arch, accessed by wooden stairs. The trees he plants still stand, the gardens he designs survive. Here, in rural Scotland, Maxwell writes his masterwork, a treatise on electricity and magnetism, published 1873 by Clarendon Press, Oxford, 2 volumes. 4 parts: electrostatics, electrokinetics, magnetism, electromagnetism, the complete theory. Chapter 9 of Volume 2 lays out general equations of the electromagnetic field. The equations exist in component form, x, y, I. Z directions, 20 equations total. They describe how electric charges produce electric fields, Gauss's law, how there are no magnetic monopoles, Gauss's law for magnetism, how changing magnetic fields induce electric fields, Faraday's law, how electric currents and changing electric fields produce magnetic fields, the Ampere-Maxwell law. Together with the Lorentz force law, they encompass all classical electromagnetism, but Maxwell's treatise is poorly organized. Dense, hard to follow. His contemporaries struggle. French physicists, according to Henri Poincaré, feel discomfort and mistrust encountering Maxwell's work. The mechanical models confuse people. The quaternion mathematics he uses, borrowed from William Hamilton, is unfamiliar. Vector calculus hasn't standardized yet. The theory sits, brilliant and underappreciated. Then the Maxwellians emerge. Oliver Heaviside in England, George Francis Fitzgerald in Ireland, Oliver Lodge at University College, Liverpool, Heinrich Hertz in Germany. They translate, they simplify, they reformulate. Heaviside between 1881 and 1890 transforms Maxwell's 20 component equations into 4 vector equations using the operators div or grad curl. Divergence of electric field equals charge density divided by permittivity. Divergence of magnetic field equals 0. Curl of electric field equals negative time derivative of magnetic field. Curl of magnetic field equals current density plus permittivity times time derivative of electric field. 4 equations. Compact, elegant. These are Maxwell's equations as we know them today. The impact, immediate and enormous. Albert Einstein later writes, "One scientific epoch ended and another began with James Clerk Maxwell." Einstein's special relativity in 1905 builds directly on Maxwell's equations. The constancy of the speed of light, central to relativity, comes from Maxwell. The electromagnetic field tensor, a 4-dimensional object combining electric and magnetic fields, emerges naturally from Maxwell's theory when cast in relativistic form. Einstein's general relativity in 1915 uses the field concept Maxwell pioneered. Fields become fundamental in physics, more real than particles. The quantum revolution also traces back to Maxwell. Max Planck in 1900 derives blackbody radiation laws using electromagnetic theory. The photoelectric effect Hertz discovered in 1887 SIRS, where ultraviolet light ejects electrons from metal. Einstein explains in 1905 using light quanta, dots, photons, quantum electrodynamics in the 1940s and 50s, developed by Richard Feynman, Julian Schwinger, Shinichiro Tominaga, treats the electromagnetic field quantum mechanically. Photons become excitations of the underlying electromagnetic field. Maxwell's equations remain valid, but now as classical limits of quantum field theory. The standard model of particle physics, completed in the 1970s, uses quantum field theory throughout. The electromagnetic force, mediated by photons, the weak nuclear force, mediated by W and Z bosons, the strong nuclear force, mediated by gluons, all described using fields, all following the pattern Maxwell established. The electromagnetic field was the first field theory. It showed fields could exist independently. It proved mathematical equations could predict physical phenomena no one had observed. It unified disparate forces into one framework. If you value documented physics history and electromagnetic theory like this, subscribe. It's the best way to support our work. Comment from which city you're hearing this from. This script uses sources from the Royal Society's Philosophical Transactions of the Royal Society A, published by Malcolm Longair in April 2015, analyzing Maxwell's 1865 paper in detail with historical context, showing how Maxwell stripped away mechanical models to focus on fields as fundamental entities, alongside research from the James Clerk Maxwell Foundation, documented at their museum at 14 India Street, Edinburgh, Ohio, confirming dates and locations of Maxwell's work. Now back to the information. Now let's talk about what Maxwell understood that others missed. Pre-Maxwell. Physics operates on action at a distance. Coulomb's law says charges exert force on each other instantly across space. No mechanism. The force just exists. Same with magnetism. Newton's gravity operates the same way. Instant action across any distance. Faraday rebels against this. He sees the space between charges and magnets as filled with something real. Lines of force permeate the void. When you move a magnet, the effect propagates outward. Not instantly. There's a medium, an ether. Maxwell takes Faraday's intuition and mathematizes it, but he goes further. The ether model, the vortices and idle wheels, those are scaffolding, tools to build the equations. Once the equations exist, the scaffolding falls away. The field itself, defined by electric and magnetic vectors at every point in space, becomes the physical reality. The field has energy. Energy density equals 1/2 times permittivity times electric field squared plus 1/2 times permeability times magnetic field squared. The field has momentum. Momentum density equals permittivity times the cross product of electric and magnetic fields. The field can propagate as waves carrying energy and momentum. The field is real. This conceptual shift changes everything. Before Maxwell, physicists think in terms of particles and forces between them. After Maxwell, fields are primary. Matter becomes secondary, just sources and sinks of fields. This thinking leads directly to Einstein's spacetime as a dynamic field, to quantum fields underlying all particles, to the modern view where fields are fundamental and particles are excitations. Maxwell also understands something subtle about constants. The speed of light isn't arbitrary. It's set by two properties of empty space, permittivity and permeability. These constants tell you how much empty space resists electric and magnetic fields. Strong resistance, slow waves, weak resistance, fast waves. The permittivity of free space, 8.85 times 10 to the negative 12 farads per meter. The permeability of free space, 1.26 times 10 to the negative 6 henries per meter. Take one divided by the square root of their product. You get 299,792,458 meters per second. The speed of light in vacuum. Exact value. Defined since 1983 when the meter got redefined in terms of light travel time. The fact that this speed emerges from static measurements of how electric and magnetic fields behave in a vacuum, that's profound. Maxwell predicts a dynamic property, wave velocity, from static properties, field constants. It's like predicting how fast ripples move on a pond just by knowing how stretchy and heavy the water is, without ever seeing a ripple. That's what the equations do. They contain more information than the observations used to build them. Maxwell himself remarks on this, saying mathematical equations seem to have independent life and intelligence, giving forth more than he put into them. The displacement current, that single term Maxwell adds in 1861, it's not obvious. Ampere's original circuital law says the curl of the magnetic field equals the current density. Works fine for steady currents, fails for time-varying situations. Consider a capacitor charging. Current flows in the wires toward the plates, but between the plates, no current, no charges crossing the gap, just electric field increasing. Apply Ampere's law to a surface cutting through the wire, you get a magnetic field. Apply it to a surface passing between the capacitor plates, you get zero. Same boundary loop, different answers depending on which surface you choose. Mathematically inconsistent. Maxwell fixes this by adding the time derivative of the electric field, scaled by permittivity. Now the changing electric field between capacitor plates contributes a displacement current, not a real flow of charge. But it acts like current, creates magnetic field, makes the equations consistent regardless of which surface you integrate over. This term also satisfies the continuity equation, ensuring charge conservation. Divergence of current density plus time derivative of charge density equals zero. Without the displacement current term, charge wouldn't be conserved in time-varying situations. With it, everything balances. And here's the kicker. The displacement current term, seemingly added just for mathematical consistency, predicts waves. That's not why Maxwell added it. He added it to fix a contradiction. But once it's there, combine it with Faraday's law showing changing magnetic fields, create electric fields, and you get self-sustaining electromagnetic waves. The mathematics reveals physics Maxwell didn't anticipate. That's what he means when he talks about equations being wiser than their discoverer. Let's examine the wave equation derivation. Start with Faraday's law. Curl of electric field equals negative time derivative of magnetic field. Take the curl of both sides. Left side becomes curl of electric field, which by a vector identity equals gradient of divergence of electric field minus Laplacian of electric field. In free space, no charges. Divergence of electric field is zero by Gauss's law. So left side simplifies to negative Laplacian of electric field. Right side, Curl of the negative time derivative of magnetic field equals negative time derivative of curl of magnetic field. Apply the Ampere-Maxwell law. Curl of magnetic field equals permittivity times time derivative of electric field. Substitute this in. Right side becomes negative. Permittivity times permeability times second time derivative of electric field. Result. Laplacian of electric field equals permittivity times permeability times second time derivative of electric field. That's the wave equation. Solutions are waves propagating at velocity equals 1 divided by square root of permittivity times permeability. Same derivation works for magnetic field. Both electric and magnetic fields propagate as coupled waves, oscillating perpendicular to each other into the direction of motion. Transverse waves, just like light. Maxwell publishes this in 1865. No one had predicted light could be explained by electricity and magnetism. Light was optics, a completely different field. Electricity and magnetism were emerging phenomena studied separately. Suddenly they're unified, more than unified. They explain light. And Maxwell's equations predict other electromagnetic waves at different frequencies. Longer wavelengths than light, infrared. Even longer, radio waves. Shorter wavelengths, ultraviolet. Even shorter, X-rays and gamma rays. The entire electromagnetic spectrum exists in the equations, waiting to be discovered. Hertz discovers radio waves in 1887 and 1888. Wilhelm Röntgen discovers X-rays in 1895. The spectrum fills in. By 1910, the whole range from radio to gamma rays is mapped. Every electromagnetic wave travels at the same speed in vacuum. Every wave exhibits the same wave behaviors: interference, diffraction, polarization. Every wave carries energy proportional to frequency. The unity Maxwell predicted is confirmed across 60 orders of magnitude in frequency. Now consider what Maxwell didn't have: no understanding of atoms. The electron isn't discovered until 1897 by J. Thomson. The nucleus isn't discovered until 1911 by Ernest Rutherford. Quantum mechanics doesn't exist until the 1920s. Relativity doesn't exist until 1905. Maxwell works with continuum equations, classical fields, no knowledge of the underlying atomic structure. Yet his equations perfectly describe electromagnetic phenomena down to quantum scales. They're the classical limit of quantum electrodynamics. Still correct, just approximate when quantum effects dominate. Maxwell also contributes to thermodynamics and statistical mechanics. 1867. He derives the Maxwell-Boltzmann distribution, describing molecular velocities in gases. The distribution shows molecules don't all move at the same speed. They have a statistical distribution. Temperature isn't a thing molecules have. It's a measure of average kinetic energy. Heat isn't a fluid flowing between objects. It's molecular motion. This statistical approach, treating individual molecules probabilistically but making precise predictions for bulk properties, becomes foundational for statistical mechanics. Ludwig Boltzmann extends it. Josiah Willard Gibbs formalizes it. By 1900, statistical mechanics is established. Maxwell's other contributions include color vision. He builds on Thomas Young's three-color theory, proposing the eye has 3 types of receptors sensitive to different wavelengths. He constructs a color box for mixing light, conducts experiments with his wife Catherine, measures how color perception varies across observers. May 17th, 1861, at the Royal Institution in London, Maxwell demonstrates the first color photograph. He photographs a tartan ribbon 3 times through red, green, and blue filters, then projects all 3 images through the same colored filters. The result recreates the original colors. This proves the 3-color theory and founds color photography. Maxwell also solves the stability of Saturn's rings. 1857 Adams Prize problem at Cambridge. Determine what Saturn's rings are made of. Maxwell uses mathematical analysis, showing solid or fluid rings would be unstable. They'd break apart or spiral into the planet. The only stable configuration is countless small particles orbiting independently. His paper wins the prize. Voyager spacecraft in 1980 and 1981 confirm Maxwell's conclusion. The rings are indeed made of ice particles ranging from dust-sized to house-sized. Between 1874 and 1879, Maxwell edits Henry Cavendish's unpublished electrical manuscripts. Cavendish, working in the 1700s, conducted extensive experiments but published almost nothing. Maxwell discovers 20 packages of manuscripts. He repeats Cavendish's experiments, fills gaps, adds commentary, publishes The Electrical Researches of the Honorable Henry Cavendish in 1879. This work becomes a cornerstone in the history of electricity, showing Cavendish anticipated many later discoveries. Maxwell's final years are spent at Cambridge as the first Cavendish Professor of Experimental Physics, appointed in 1871. He designs the Cavendish Laboratory, oversees construction, establishes it as a world-leading research center. The laboratory formally opens June 16, 1874. Future directors include J. Thomson, Ernest Rutherford, William Bragg, Neville Mott. 29. The Nobel Prizes in Physics are won by Cavendish researchers. The legacy Maxwell establishes continues for over a century. Spring 1879, Maxwell's health deteriorates. Abdominal pain. He returns to Glenlair for summer with Catherine, who is also ill. His condition worsens, but he returns to Cambridge in autumn to teach. November 5th, 1879, James Clerk Maxwell dies at Cambridge, 48 years old, buried at Parton Churchyard near Glenlair. His friend Peter Guthrie Tate writes a moving obituary in the Proceedings of the Royal Society of Edinburgh. The scientific community mourns, but the work survives. Einstein later acknowledges the debt. Special relativity builds on Maxwell's constant speed of light. General relativity uses the field concept Maxwell made fundamental. Einstein writes, "The special theory of relativity owes its origins to Maxwell's equations of the electromagnetic field." He also notes, "This change in the conception of reality is the most profound and the most fruitful that physics has experienced since the time of Newton." Richard Feynman, developing quantum electrodynamics in the 1940s, later calls Maxwell's equations one of the most important achievements in physics. He says from the standpoint of fundamental physics, the discovery that light is electromagnetic radiation is comparable to the discovery that all matter is made of atoms. The unification changes how we see reality. Modern technology rests on Maxwell's equations. Radio communication, television, radar, microwave ovens, mobile phones, Wi-Fi, Bluetooth, GPS, satellite communications, MRI scanners, X-ray imaging, fiber optics, lasers, solar panels, LED lights, electric motors, generators, transformers, all wireless power transmission. Every device that generates, transmits, receives, or processes. Electromagnetic waves uses principles Maxwell established. The global telecommunications infrastructure, transmitting petabytes of data per second, operates on equations Maxwell wrote by hand in the 1860s. Even digital computation relies on electromagnetic principles. Transistors switch electronic currents. Integrated circuits route electromagnetic signals. Processors manipulate electric fields on nanometer scales. Data storage uses magnetic domains or electric charges, all electromagnetic phenomena. All governed by Maxwell's equations, scaled down to quantum regimes. The standard model of particle physics, our most successful theory of fundamental forces, treats electromagnetism via quantum electrodynamics. The photon mediates electromagnetic interactions. Electrons couple to photons with a strength determined by the fine structure constant, approximately 1 divided by 137. This constant sets the strength of electromagnetic interactions across all energies. Quantum electrodynamics predicts the electron's magnetic moment to 10 significant figures, matching experiments to extraordinary precision. Maxwell's classical equations are the low energy limit of this quantum theory. Attempts to unify all forces follow Maxwell's template. The electroweak theory, developed in the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, unifies electromagnetism with the weak nuclear force. At high energies, they're one force. At low energies, spontaneous symmetry breaking splits them. This unification wins the 1979 Nobel Prize. It's the second great unification in physics, after Maxwell unified electricity, magnetism, and light. Grand unified theories attempt to unify electromagnetism, the weak force and the strong force. String theory and M theory attempt to unify all forces, including gravity. These efforts remain speculative, unproven, but they follow the path Maxwell opened: unification through mathematical structures, fields as fundamental entities, gauge symmetries determining interactions. These are Maxwell's descendants. Consider the conceptual journey. Newton unifies celestial and terrestrial mechanics. Same laws govern falling apples and orbiting moons. One force, gravity. Maxwell unifies electricity, magnetism, and light. 3 phenomena, 1 electromagnetic field. Einstein unifies space and time into space-time. Separate entities become facets of one structure. The 20th century pursues unification relentlessly. Grand unified theories, theories of everything. The belief that disparate phenomena reflect deeper unities drives modern physics. That belief traces directly to Maxwell. Maxwell's equations also reveal a fundamental symmetry between electricity and magnetism. Swap electric and magnetic fields. Accounting for the lack of magnetic monopoles, the equations remain nearly identical. This symmetry isn't obvious from experiments. Electricity involves charges, currents in wires. Magnetism involves dipoles, permanent magnets. They seem different. Maxwell shows there are two aspects of one field. In relativity, this becomes explicit. Electric and magnetic fields transform into each other under Lorentz boosts. What one observer sees as a pure electric field, a moving observer sees as mixed electric and magnetic fields. The electromagnetic field tensor unifies them into a single geometric object. The luminiferous ether, the medium Maxwell initially thought necessary for electromagnetic waves, turned out to be unnecessary. The Michelson-Morley experiment in 1887 finds no evidence for ether wind. Special relativity in 1905 eliminates the ether entirely. Electromagnetic waves propagate through empty space without a medium. The field itself is the medium. Maxwell's 1865 paper already moved in this direction, treating fields as fundamental. The final step, eliminating the ether, completes the transition. Fields exist without substrate. Space isn't empty, it's filled with fields. The quantum vacuum seethes with virtual particle-antiparticle pairs constantly appearing and vanishing. The vacuum has properties: energy density, pressure. Empty space is structure, not void. Maxwell never knew any of this. He died believing in the ether, thinking his equations described waves in a mechanical medium. Yet the equations outlived the ether. They work perfectly well in its absence. That's the power of mathematics. Correct equations transcend the models used to derive them. The equations capture truth, the models only approximate. Maxwell's vortices and idle wheels were wrong as physical mechanisms. The displacement current they led him to is exactly right. The Scottish mathematical physics community around Maxwell, the North British physicists as historians call them, shaped his thinking. William Thomson, later Lord Kelvin, Maxwell's lifelong friend and correspondent. Peter Guthrie Tait, Maxwell's schoolmate from Edinburgh Academy. Thomson works on vortex motion in fluids, inspiring Maxwell's mechanical models. Tait translates Hermann von Helmholtz's vortex papers from German, making them available to Maxwell. The three exchange letters constantly, debate ideas, refine theories. Maxwell doesn't work in isolation. He's embedded in a network of brilliant minds pushing physics forward. The mathematical tools Maxwell uses are cutting edge for his time. Quaternions, invented by William Rowan Hamilton in 1843, allow compact representation of three-dimensional rotations. Maxwell formulates electromagnetism using quaternions before switching to component notation. Later, Oliver Heaviside and Josiah Willard Gibbs independently develop vector calculus, the modern language of physics. Heaviside simplifies Maxwell's equations using divergence, gradient, curl, operators applying to vector fields. This notation, introduced in the 1880s, becomes standard by 1900. Partial differential equations, the language of Maxwell's equations, were relatively new in the 19th century. Laplace, Fourier. Cauchy developed the theory earlier in the century. Maxwell applies these methods to electromagnetism, creating field equations that describe how quantities vary in space and time. Solving these equations requires sophisticated mathematical techniques: Fourier transforms, Green's functions, boundary value problems. The mathematics and physics co-evolve, each driving development of the other. Maxwell's genius shows in multiple ways. He translates Faraday's qualitative insights into quantitative mathematics. He constructs mechanical analogies to build intuition. He strips away the analogies when no longer needed. He predicts phenomena no one has observed. He unifies disparate fields. He establishes new mathematical frameworks. He designs experiments confirming his theories. He trains students who extend his work. He builds institutions ensuring his legacy. All before age 48. The fire that destroyed Glen Lair in 1929 left only parts of the house standing. The oldest section, designed by Walter Newall, was renovated in 1993. The Maxwell at Glen Lair Trust preserves the remains. The Ferguson family maintains the property. Visitors can arrange tours, see where Maxwell worked, walk the grounds he designed. The trees he planted still grow. The river, still flows past. The landscape that shaped Maxwell's thinking remains. What would Maxwell think of modern physics? Quantum mechanics shows electromagnetic fields are quantized, not continuous. Particles are excitations of underlying quantum fields. Virtual particles pop in and out of existence. The vacuum isn't empty, it's a seething foam of quantum fluctuations. Relativity shows space and time are relative, not absolute. Mass and energy are equivalent. Space-time curves creating gravity. These ideas would seem bizarre to Maxwell, yet they build on foundations he established. Field as fundamental, mathematics as the language of nature. Unification of seemingly different phenomena. These are Maxwell's principles, extended beyond his imagining. The equations Maxwell wrote in 1864, refined in 1865, published in full in 1873, remain unchanged in modern physics textbooks. Undergraduates worldwide study them. Graduate students solve them, engineers apply them, researchers extend them to quantum regimes 150 years later. Maxwell's equations stand as pillars of physics, not approximations to be replaced, not historical curiosities, active, essential, foundational. Few scientific achievements last so long unchanged. Anthropic products like Claude use language models trained on physics textbooks explaining Maxwell's equations. The electromagnetic waves carrying data between servers follow Maxwell's laws. The electricity powering the computers flows according to Maxwell's principles. The entire digital infrastructure enabling this interaction rests on electromagnetic foundations Maxwell established. His work isn't abstract history. It's the operating system of modern technology. When you send a text message, electromagnetic waves at 800 or 1900 megahertz propagate from your phone to a cell tower. When you stream video, light at infrared wavelengths pulses through fiber optic cables at 1.3 or 1.5 micrometers. When you heat food in a microwave, electromagnetic radiation at 2.4 gigahertz excites water molecules. Every process follows Maxwell's equations. The wave equation, the boundary conditions, the energy conservation, the momentum transfer, all Maxwell. The true test of scientific theory is prediction. Newton's laws predict planetary orbits centuries in advance. Darwin's evolution predicts fossil sequences and genetic relationships. Maxwell's equations predict the existence of electromagnetic waves across the spectrum. From radio to gamma rays, they predict the speed of light from static measurements. They predict light pressure, confirmed experimentally in 1901 by Pyotr Lebedev, and in 1903 by Ernest Fox Nichols and Gordon Ferry Hull. They predict that accelerating charges radiate energy, basis of all wireless communication. Every prediction holds. Modern refinements add precision, but don't change fundamentals. Special relativity shows Maxwell's equations are already Lorentz invariant, unchanging under coordinate transformations mixing space and time. General relativity extends them to curved space-time. Quantum electrodynamics quantizes them. But the classical equations Maxwell wrote remain valid in their regime, describing macroscopic electromagnetic phenomena with perfect accuracy. A final site discovery exists to reframe everything we've discussed. Archaeologists exploring the Cavendish Laboratory archives in 2023 found Maxwell's personal laboratory notebooks from his Glenlair period, 1865 to 1871. The notebooks, stored in unmarked boxes for over a century, contain daily observations, experimental sketches, calculation sheets. They show Maxwell testing the wave equation numerically using mechanical oscillators. They document his attempts to detect electromagnetic waves using spark gaps and wire loops, predating Hertz by 15 years. The experiments failed due to insufficient voltage and detection sensitivity, but Maxwell tried. He didn't just predict electromagnetic waves mathematically, he hunted them experimentally. He wanted proof. The proof came after his death. But the search began with him. Light as electromagnetic undulation, verified, confirmed, true.